Analytical Chemistry 1, Lesson 39. We know now how to calculate a titration curve. We know the general shape. We know how the shape changes with concentration and equilibrium constants. But of course, in real life, we do not take the parameters of a chemical system and calculate its titration curve. We acquire a titration curve and determine the chemical parameters from it. The key parameter to measure is the equivalence point. How much titrant was added to reach the equivalence point? The modern approach to titration is to use a pH meter attached to a computer and an auto titrator attached to the same computer. The computer can then acquire an accurate record of pH as a function of added titrant. But how would you go about determining the equivalence point from such a curve? Here again is the titration curve we saw in the last lesson. Instead of knowing the result, we will use this graph to determine what we want to know about this unknown powder. We added 0.1329 grams and dissolved it to make a 20 milliliters of solution. We titrated it with a 0.05 molar solution of sodium hydroxide. The solution pH started low and increased. We can conclude that it is an acid. Looking closely at the curve, there appear to be two equivalence points. The first is rather blurred, while the second is quite sharp. Is the second exactly twice the volume of the first? If so, it would be a diprotic acid. But could it be a mixture of two acids whose concentrations are close but not exact? Hard to say when the first endpoint is so blurred. We can expand the graph around the sharp transition. By estimating by eye the inflection point of the curve, we can draw a straight line down to the x-axis and declare the equivalence point to be at 32 milliliters. Such an eyeball estimation is the first approach to identifying the equivalence point. This is the region around where we thought the first inflection point occurred, but it is rather pointless to try to guess where it is located here. Is there a better way? Well, the answer lies with differential calculus. The first derivative of a curve, dy by dx, is the slope of the curve at each point. If the curve is flat and parallel to the x-axis, the derivative is 0. If it is rising to the right, it is positive. If it starts to rise more quickly, the derivative is larger. But our curve is not continuous, nor is it a function that we can differentiate. We only have discrete values, the data points, that were acquired during the titration. With our discrete data points, we can estimate the derivative with delta y over delta x. Here are the first 10 data points on the curve. Take the first two x values, the titrant volume, and find the midpoint between them. Now that's just their average. This will be the x values for our derivative plot. We place it in the next column. Continue this down with each pair of data points. Go back to the top. Take the first two data points again. Take the difference in pH and divide it by the difference in volume. Be sure the delta pH is pH2 minus pH1 and delta V is V2 minus V1. Divide them and put the result beside the first midpoint volume. Continue down for all pairs. The first two columns form the graph of our titration data, and the next two columns will form a graph of the first derivative of our data against volume. Here is our original curve with the first derivative curve added on top of it. The derivative curve is the brown curve. Note the large peak that corresponds exactly with the large equivalence point. Finding the peak of this curve is easier than trying to determine the point of inflection. It is easier to find the equivalence point this way. You can also see another small peak where we believe there is a first equivalence point, but finding the peak maximum remains difficult. It is still not clear where the first peak is located. Look at the curve again. As it approaches the equivalence point, the slope increases. This is why the first derivative becomes large. But right at the point of inflection, right at the peak of the first derivative curve, that's where the slope now starts to decrease. The first derivative curve starts to go down again. What is the slope of the first derivative curve doing? Well, the slope is positive, increasingly, so as it approaches the peak. But then suddenly it becomes negative as it goes down the other side. The derivative of the derivative goes through 0 at the point of inflection. The second derivative, going to 0, is defining the point of inflection. Take the second derivative of our data, titration data, by taking the derivative of the first derivative of the data in the same way. Here's the graph of our titration data along with the first and second derivative curves. Notice how the second derivative plunges through the x-axis right where the point of inflection is. This is much easier to determine the equivalence point. Now let me expand the graph in the region of the second equivalence point. Now this is just the region from 30 to 35 milliliters of added titrant. Notice how the second derivative curve, now I've made it thicker so you can see it, goes right through the x-axis at 32 milliliters. This is an excellent way to find the equivalence peak point. Well, what about the smaller peak? Well, no, this still doesn't help much. But go in and multiply the second derivative data by some scaling factor to blow up the curve. What do you get? Now that's it. I scaled it by a factor of 50. It goes through the x-axis 0 at exactly 16 milliliters. The first equivalence point is exactly 1/2 of the second equivalence point. This is definitely a diprotic acid. So what else can we find out about it? From the known concentration of the titrant and the volume added at the equivalence points, we know the moles of added titrant and therefore the moles of the original acid. Because the two equivalence points are equal, we know they relate to the same diprotic molecule. In this case, we see that there are 0.8 millimoles of base added to reach each equivalence point, implying that there was 0.8 millimoles of acid present originally. We know that the original volume of the acid was 20 milliliters. Therefore, we can calculate that the original concentration of the acid was 0.04 molar. We know the mass of added acid was 0.1329 grams, so we can determine its molar mass now. It is 166.13 grams per mole. Here's another piece of information. We know the two equivalence points, and their average is at 32 plus 16 divided by 2 is 24 milliliters. Here is a greatly expanded view of the graph in the region around 24 milliliters. I've scaled the y-axis to increase the resolution of our view of that region. Draw a line up from the 24 milliliter mark and then from there over to the y-axis. We found earlier that at the midpoint of the buffer region, the pH is equal to the pKa. So for this sample, the second pKa is around 5.41. We can look through tables for a diprotic acid with a second pKa around 5.41 and then check to see what its molar mass is. We are led to conclude that the unknown sample must be benzene 1,2-dicarboxylic acid, whose common name is phthalic acid. This approach, using the second derivative of your data, can have issues because it depends upon having good data right near the equivalence point. Yet because the pH is changing quickly in this region, there is less data and it is harder to get stable results from a pH meter. To help with this, another approach has been developed to interpret titration curves. It utilizes data from well before the equivalence point and can be more accurate. It is called a Gran plot. Here is the acid dissociation constant. We include activity coefficients explicitly this time. Now, prior to the equivalence point, a strong base, the titrant, will react virtually completely to convert a weak acid into its conjugate weak base. Here are some definitions. The weak acid, the analyte, has an original formal concentration of FHA in it. The strong base titrant has a formal concentration of F sub B. The analyte solution has an original volume of VHA in it. And at any point in the titration, there's a known volume of added titrant, VB add. At any point in the titration, the concentration of weak base is related to the amount of added titrant. This is just a dilution that equates the moles of added strong base titrant to the moles of conjugate weak base produced divided by the total volume. At the same time, the concentration of weak acid is that which is left from the original and similarly diluted. Substitute these into the Ka expression. Note that the denominators cancel. Reorganize the terms to get this expression. Note that the concentration of hydronium times its activity coefficient is exactly the response that is given by the pH meter. Rearrange the terms in brackets. The numerator of the first term in parentheses is just the moles of initial analyte. When divided by the titrant concentration, this is the definition of the volume of added titrant to reach the equivalence point. The first term in parentheses is just the equivalence point volume. We now have the Gran plot equation. Graph VB add times 10 to the minus pH versus VB add. When VB add equals V equivalent, this goes to 0. We don't normally use all of the titration data, perhaps 10 to 20% of the data before the equivalence point. The equation is that of a straight line. Near the equivalence point, The experimental data starts to curve off. 10 to the minus pH never goes to 0. But it is easy to extrapolate a straight line from the rest of the curve down to the x-axis. This is the equivalence point. In practice, there can still be some curvature because of changes in the activity coefficients for the weak acid and its conjugate base. The ionic strength of the solution is changing during the titration. Sometimes this is compensated for by adding another non-reactive salt to swamp the effect of the smaller changes. One might add sodium nitrate, for instance, at a concentration much greater than the analyte. Then changes in ionic strength will be small. The activity coefficients may be unknown, but they will be constant throughout the titration and only affect the slope of the plot, but not the intercept. Here is a grand plot of the data approaching the second equivalence point. The data is particularly smooth because it's synthetic data. Real data would have more scatter and curvature. Now, when we draw a straight line through the data, as advertised, it passes through the x-axis at the equivalence point of 32 milliliters. When you have acquired some titration data, you have several tools at your disposal to help you determine the equivalence points and analyze your sample as needed. You might eyeball it when the transition is steep and well-defined. You can use either first or second derivative data to find them, or perhaps use a grand plot. Together, you can effectively determine the properties of an unknown acid or base.